Hello guys, a big thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.
Hello guys, my name is IBM and today I'm taking you to circular motion, and I think this is lesson number 2. Having seen some of the concepts in lesson number 1, we were able to explore the introduction part to circular motion, where we were able to derive some of the quantities that we may need in circular motion. And those were the most common concepts where we derived an expression for, we actually defined angular velocity, where we said angular velocity omega was delta theta by delta t, the rate of change of angular displacement. We defined angular displacement as the arc ratio of the arc length to the radius. We were able to derive v equals to omega times r. We were able to notice that the period T or omega was equal to 2 pi over t, and of course we were able to establish that omega is also the same as 2 pi times f. So we used these quantities in lesson 1. So in lesson 2, I want us to take this further and try to understand more details about or more details in circular motion. And I think in lesson 2, we shall concentrate mostly on centripetal acceleration and centripetal force. So let's go to lesson number 2. So in lesson 2, we are going to explore more about centripetal force and centripetal acceleration. So let's imagine that you were whirling a rubber band on the end of a string in a horizontal circle. Of course, we shall later on see that circles are of two types. We have the vertical circle and the horizontal circle. So imagine whirling a rubber band on the end of a string in a horizontal circle above your head. Remember, this is circular motion. So we are trying to make it go around in a circle. So in order to make it go around in a circle, you have to pull on the string towards the center of the circle. In case you let go of the string suddenly, then there will be no tension in the string because you have stopped pulling towards the center of the circular path. So there is no tension in the string and the band will fly off at a tangent to the circle. So the band would fly off at a tangent to a circle. So this is what exactly I'm demonstrating here. If you try to while a rubber band in a circular path above your head. This is what we call a horizontal circle. This demonstration is the circle has been drawn in a horizontal plane. Of course, there is also a vertical circle, as we shall see later on. So, in case you let go of the string, observations show that the band will move at a tangent to the circle. It will fly off at a tangent to the circle. If the bang was, for example, it was at this point here, motion is clockwise, then it would first move off at a tangent to the circle. If the bang was somewhere here, it would first move off at a tangent to the circle. And if it was here, because motion is clockwise, it will first move vertically upwards at a tangent to the circle. So in all cases, we are saying it moves at a tangent to the circle. So this object is describing circular motion, but it's like there is a force at the center of the circle which is trying to keep it to continue moving in its circular path. That when that force is lost, the circular path is also lost. The object will no longer continue moving in a circular path. So similarly, that is how the Earth orbits the Sun, or how other planets orbit the Sun. As the Earth orbits the Sun, it has a constantly changing velocity. Why? Because the direction of motion keeps changing. After all, velocity is a vector quantity, and if velocity is a vector quantity, even if the magnitude, which can be the speed, remains constant, the velocity would be considered to be changing because it also depends on the direction. So if the direction changes for a body moving in a circle, then we say velocity is changing. And according to Newton's first law, it suggests that there must be unbalanced forces acting on it. As long as the velocity is not constant, then there must be unbalanced forces acting on it. So the resultant force is most likely going to be the centripetal force for the body moving in a circular path. Okay, so as the Earth orbits the Sun, it has a constantly changing velocity because the direction is changing. And Newton's first law suggests that there must be unbalanced force acting on it. That's why there is a change in velocity. If there is no unbalanced force, we don't expect any acceleration, and therefore we don't expect the velocity to be changing. But even though when the speed remains constant, since there is a change in direction for an object moving in a circle, then you and me can agree that there must be an unbalanced force. There must be a resultant force acting on this body. In fact, that force is going to be the pull of gravity towards the Sun. So it's like the Sun must be exerting a resultant force onto this Earth. So that means that resultant force is the one which is keeping the planet or the object, the planet, the Earth, to continue orbiting around the Sun. So the gravitational pull of the Sun is responsible for keeping the Earth to continue orbiting around the Sun, and also to keep other planets to continue orbiting around the Sun. So that unbalanced force is responsible for providing an acceleration, or for providing a change in velocity, which results into an acceleration that we shall later on call the centripetal acceleration. And theories predict that if that force disappeared, if that force was to be lost, if the gravitational pull would be lost, say if the Earth is in this position indicated in the diagram, and the gravitational pull is lost, then the Earth would continue in a straight line in that direction at a tangent to the path where it was. If the Earth was somewhere here and the gravitational pull of the Sun is lost, then it would continue at a tangent in that direction until maybe it reaches into another gravitational field, or another gravitational field comes into play. So there is a force which is responsible for keeping objects to continue moving in a circular path, and that force is responsible for the acceleration of the object because there is a change in velocity. Since for an object moving in a circular path, even if the speed remains constant, the change in direction means there is a change in velocity. Therefore, that unbalanced force cannot be ignored. We need to note a few things here then. A few things we need to note. Number one, remember Newton's first law of motion. It tells us that an object with a resultant force of zero acting on it will either not be moving, it will not be moving at all, or it will be moving in a straight line at a constant speed. So there are two options here according to Newton's first law. Either the object is at rest, where the resultant force is zero, or the object is moving in a straight line at a constant speed. But then this object is moving in the first place. It is not at rest. And second, it is not moving in a straight line. It is changing direction. And because it is changing direction, then the velocity must be changing. But if it was moving in a straight line, then the velocity would remain constant if the speed was constant. So it implies or it tells us that even if a body in a circular motion moves at a constant speed, even if the speed remains constant, this body is going to be said to be accelerating. Even if a body in a circular motion moves at a constant speed, it is going to be said to be accelerating. Why? I have mentioned that while moving in a circular motion, there is a change in direction. Acceleration is the rate of change in velocity. Velocity is a vector quantity. It doesn't only depend on the magnitude. When we say the speed is constant, we are meaning that the magnitude is constant because speed is the magnitude part of velocity. So the magnitude is constant, but there's a change in direction for every object moving in a circle. So a change in direction is just enough to tell us that the velocity is changing, and therefore, a body moving in a circular path at a constant speed can still be considered to be accelerating. The examiner may ask you to explain why, for a body moving in a circular path, it is said to be accelerating even when the speed is constant. So this is how we explain this. An object traveling in a circle may have a constant speed but is not traveling in a straight line as predicted by Newton's first law. Because for the first law, the body is either at rest if the resultant force is zero, or it is moving in a straight line at a constant speed. But this one is not at rest in the first place. It is moving. Number two, it is not moving in a straight line. That means even if the speed is constant, the velocity cannot be considered constant. So the velocity is changing as velocity is a vector quantity because velocity depends on magnitude and direction. We can consider the magnitude to the speed to be the magnitude part, which is constant. But there is a change in direction because for a body moving in a circle, there is no way it can be moving in a circle without changing direction. The direction continues changing around the circle. So a change in velocity means the object is accelerating. Because there's a change in direction, the velocity is changing. And a change in velocity means the object is actually accelerating. But in which direction is the acceleration? The force responsible for causing this change in velocity is acting towards the center of the circular path, as we have seen with the Earth rotating around the Sun. The gravitational pull is acting towards the center of the Sun, and from Newton's second law, force is equal to ma, the resultant force and the acceleration are always in the same direction. So it means the acceleration responsible is always going to be towards the center of the circular path. The acceleration is going to be towards the center of the circular path, and we shall call this acceleration the centripetal acceleration. So the acceleration is going to be called centripetal acceleration. So for a body moving in a circular path at a constant speed, it keeps changing direction. Velocity being a vector quantity, a change in direction means a change in velocity. And a change in velocity means the body is accelerating. The acceleration acts towards the center, and we shall call it centripetal acceleration. The word centripetal, these are two words, centri, which is center, and repetal, which means seeking. The acceleration seeks the center. Petal means seeking, centri means coming from center. So centripetal, the acceleration seeks the center, so it is always acting towards the center. That's why we are going to call it centripetal acceleration. Okay, so so we now know why a body moving in a circle is considered to be accelerating. We now know why a body moving in a circle accelerates, and we have said because of the change in direction, the body continues changing direction. Even if it is moving at a constant speed, a change in direction is enough to mean that the velocity has changed, and a change in velocity implies that the body is actually accelerating. So in order to make an object accelerate, there must be a resultant force acting on it, because there can't be an acceleration when there is no resultant force acting on the body, according to Newton's third law. And this resultant force is what we are going to call the centripetal force. The acceleration was called centripetal acceleration, and the resultant force is going to be called the centripetal force. Why is it called centripetal? It's only because it acts towards the center. It seeks the center. So the centripetal force, just like the centripetal acceleration we have mentioned, the centripetal force acts towards the center of the circle in the same direction as the acceleration, as predicted by Newton's second law. So what is the implication of this? If the center is somewhere here and the object is moving in a circular path anticlockwise, the acceleration is towards the center, the centripetal force is towards the center, and we say that object is moving at every point is moving at a tangent. The reason as to why the force does not change the speed is always because the object moves at a tangent to the circular path. Therefore, the force does not change the speed, it just changes the direction. So the object is going to be continuously moving at a tangent to the radius of the circular path. Therefore, we simply say that this means that the centripetal force always acts at right angles to the instantaneous velocity, or to the velocity at that particular point. It always acts at right angles to the velocity, or the velocity is always at a tangent to the centripetal force. The velocity is always at a tangent to the circular path. That's what we call centripetal force and the motion of the object moving in a circular path. A few things we need to note here. Number one, for the ball on a string, for example, which is being swung in a vertical circle, if it is being moved in a vertical circle, if you don't know what a vertical circle is, at some point the object must be below, at some point should be above you. Maybe if you have put an object on a string and you try to move it in a vertical circle. So for the ball on a string which is being swung in a vertical circle, it is, remember, on a string. There must be a force in this string here, which in most cases is going to be the tension. Just like we saw that the gravitational pull of the sun on the earth was responsible for keeping the earth orbiting around the sun. Then for an object attached on a string, then the only force in the string must be tension. So we normally simply say it's the tension which is going to provide the centripetal force and therefore provide the centripetal acceleration. So it's the tension, like in the previous slide, is the tension which is going to provide the centripetal force and therefore the centripetal acceleration. And at any instant, we have already seen that the ball's direction, or the direction of the ball's velocity, is always at a tangent. If the ball is here, then the velocity is at a tangent to the circle. In other words, it makes 90 degrees with the radius. If the ball is somewhere here, then the velocity is at a tangent to the radius. So at any instant, the direction of the ball's velocity is along a tangent to the circle, as shown as shown above, or as we have seen in the previous slide. And if the string breaks or is released, there will be no longer tension in the string, and this would mean that the centripetal force is being lost. So if the string is broken or it is released, there will be no longer tension. Nothing is pulling onto the body towards the center. And if there is no tension, then we say the centripetal force has been lost. What is the net effect, or what will be the immediate impact? In that case, if the centripetal force is released, then the ball will travel in the direction of the tangent to the circle at that particular moment of release. If the ball is at this point at the bottom of the circle, it is moving at a tangent to the radius. So if the string is broken when it is in this position, then the ball is expected to continue in that direction of the tangent. If the ball was at the top of the circle and the string is broken, we would expect the ball to continue at a tangent because it was moving in that direction at that moment when the string is released or when the tension is being lost. So when a body moves in a circular path, if the centripetal force is lost, then it is going to continue moving in a circular path. I mean, it is going to continue moving in a straight line at a tangent to the circle at that particular point, at that particular moment. That's what we call centripetal force and centripetal acceleration that we are discussing here. Okay, so let's now see the relationship between centripetal force and centripetal acceleration. Do not forget, according to Newton's second law, the resultant force on a body is equal to mass times acceleration, which would therefore mean, because the resultant force here is the centripetal force, we shall use Fc for centripetal force. This will be mass times Sc for centripetal acceleration. So by Newton's second law, the centripetal force is equal to mass times the centripetal acceleration. Let's begin by deriving an expression for the centripetal acceleration. Of course, you will not be asked to derive this expression, but you'll always use it for calculations. We are going to derive an expression for the centripetal acceleration. So we are going to consider a body moving in a circular path. I'll just pick a diagram for a body moving in a circular path as shown here. Let's say the body was at t equals to 0. Let us assume that the body was at position at point A, and after a certain time, let's say the body is at point B. Let's say after a certain time, let me call that time maybe delta t. After a small time delta t, I will assume that the body is at point B. So it has moved through a curvilinear distance, which is A to B. I'm going to consider this object to have a mass m. Let the mass of the object be m. All right, I'm going to be forced to write in this diagram. So let's say the mass is m, and the radius of the circular path is of course r, as shown in the diagram. And we are going to say the constant speed with which it moves in the circular path is going to be v. So speed, which is the curvilinear speed, the constant curvilinear speed is v, as we saw before. And we are assuming that it moves from A to B in a time delta t. So I can draw what we call a vector diagram from this. So I just prolonged this and I prolonged that. And if you're a mathematician, you notice that if this is 90 degrees and this is 90 degrees and this angle is theta, this angle is going to be, I think this is 180 minus delta theta, which means the other angle is going to be delta theta. Like I said, you're not to be asked to derive this. So this angle is delta theta. Remember, this is velocity at point B, and this is a velocity at point A. So this is still VA. So I'm going to just draw a vector diagram. I'm going to come up with a vector triangle. I want to come up with a simple vector triangle. So I'll just take this backwards. Let me start by drawing the vertical. Of course, to draw a vector diagram, you have to fix one vector. So I'll fix this one, and I will reverse. Remember, vectors are joined head to tail. We join vectors head to tail. We are trying to find the resultant velocity from A to B. So we join the vectors head to tail. So I'm going to fix this one here, which is VB. Remember, VA was to the right. I'm going to reverse it. If I fix VB, that is VB on its head, I must add the tail of another vector. So VA was to the right. So if I fix it here, I cannot join head to head. It must be head to tail. So this would be negative VA. So this is now a continuous anticlockwise loop. So the resultant is supposed to be the other way around. So the resultant is going to be a vector which is in this direction here. So this will be the resultant, which we are going to call the change in velocity delta V. So this angle here is the same as, if I take this down, it is the same as this angle here, which is delta theta. So this angle is delta theta. Therefore, I will come up with a simple diagram like that. So I have reversed the vector which was to the right, which is VA, and is now in this direction. I've maintained VB in that direction, and I'm saying the resultant is in this direction, which is going to be the change in velocity. So at A, the velocity is VA, and at B, the velocity is VB. Both VA and VB are going to be vectors because they are pointing in particular directions. And the change in velocity is going to be seen from this vector diagram here. So a vector delta V must be, if I want to find VB, I must add delta V to negative VA to find VB. In order to find VB, I get this plus negative VA to get the other one, which is the same as saying that delta VB is the same as, because to find VB, I would say delta V or change in V plus negative VB should give, plus negative VA should give me VB, which is the same as saying delta V is the same as VA plus VB. It is the same thing. So I want you to also notice that the triangle that I've drawn here, which is ECD or CED, and the triangle, if I draw this triangle here, let me just complete a triangle here. I'm going to just draw a triangle here. Remember, I'm assuming that AB is a very small, delta theta is a very small angle, that the arc length can be approximated to a straight line. So this, because the angle here is delta theta and the angle in this is also delta theta, and these two are equal in magnitude, VA and VB are equal in magnitude, yet here we had R and here R, it means these two triangles are going to be similar. So the triangles AOB and CED are actually similar. And if they are similar, then I can use similarities. I can use similarities. For example, I can say BA, of course, BA matches with ED, I think. So I will say BA divided by maybe the radius, which is OB, is going to be equal to, I took BA and one of the radius, which is OB. This is going to be the same as the matching distance is going to be DE or ED. So this is the same as DE divided by one side where we have, I can say DC, because they are going to be equal. And also, I want you to recall that the angular displacement delta theta was equal to delta S, or the arc length over the radius. Also remember, the angular displacement was delta S over R, which was the same as, or which is the same as, let me just say the distance here is approximately equal to the arc length. But I want you to also, that is if delta theta is very small, but I want you to also notice that the angular displacement delta S over the radius is actually the same as delta V or the change in velocity divided by VB. Because BA is approximately equal to the arc length, I can call that delta S. And OB or BO is the same as the radius, I can call that R. DE is the change in velocity, which is delta V, and DC is VB. So I can take this to be as something like this, just if I simplify. If I make delta V the subject, because I'm interested in the change in velocity, so delta V is going to be equal to delta S, which is the arc length, then times VB divided by R. So delta S over R equals to dV over VB. It means dV, or the change in velocity, is delta S times VB over R. That is, I just made the change in velocity the subject. So remember I said the time taken for the body to move from point A to B was delta T. So I'm going to divide both sides by delta T. So divide the left hand side by delta T, divide the right hand side by delta T. So when I divide change in velocity over time, I think that is automatically acceleration. So this is going to be acceleration. But because the body was moving in a circular path, this acceleration we call it the centripetal acceleration. And you also remember from the previous part, the arc length over time, or the change in length, or the distance over time is actually linear speed. So this is going to be V. So that is the curvilinear speed or curvilinear velocity V. And so this is going to be V into VB over R. But I want you to also remember that the speed is constant, so it means VB is the same as VA, which we shall just call V, which means now that the acceleration FC is going to be V times V divided by R, which becomes V squared over R. So I have just used a similarity. There is a curriculum where students could be asked to derive that, so I will repeat this. I will just rub off all this, and I try to repeat this for those students. So sometimes you could be given the diagram. Of course, you cannot start from zero. You could start from a diagram for a body moving in a circular path. So this is what I mentioned, or this is what I said, that having come up with a vector triangle by joining head to tail, I said maybe I would rub off this part here so that students can also see it clearly. Vectors are supposed to be joined head to tail, and I prolonged the VA and I prolonged the VB, and they met at this point, and I say this angle here was the same as this one here, because if you use your mathematics, if this is 90, this is 90 because these are tangents, and this is delta theta. Of course, the angle sum of the whole polygon is going to be 360, which makes this one to be 180 minus delta theta. Then if I consider a straight line, the angle sum of a straight line is 180, so this angle is delta theta. But if I take this downwards, you notice that this angle here is the same as this one here, so this is delta theta. But remember, this one is V, this is VB, and this one was VA. But then in the vector diagram, I reversed because vectors are supposed to be joined head to tail. So I reversed VA to point in the opposite direction. So the angle here is the same as that. And these vectors, remember, have the same magnitude. VA is the same as VB, and we can say it is just equal to V because the speed remains constant, but only there is a change because there is a difference in direction. Okay, so I say this triangle is therefore similar to this one, but remember AB we assume that this delta theta is very small, so that the curvilinear distance is approximately the same as the straight line from A to B. Of course, in this diagram, it is exaggerated just for learning purposes. Therefore, I said using similarities, I said AB or BA divided by say BO is equal to the corresponding sides are going to be DE divided by maybe DC. So I substitute AB is approximately the same as the curvilinear distance, which we call delta S. This arc length is delta S. Divided by BO is the radius, which is R, and DE is the change in velocity, delta V, and DC was the velocity, VB. Then we made change in velocity the subject, delta V was equal to delta S times VB divided by R. Then we said this takes place in a time delta t, so I divided both sides by delta t. So by delta t, the other side by delta t. And we said change in velocity over time is acceleration, but because this is a body moving in a circle, we call this the centripetal acceleration A subscript c. So A subscript c is going to be delta s over delta t. This is distance, curvilinear distance divided by time. That is actually curvilinear speed, which is v. Then we multiply this by VB over VR. Remember, VB is the same as VA, is the same as V because just it is constant. So this is times V over R. And therefore, we conclude by saying that centripetal acceleration is V squared divided by R. In the Cambridge paper 4, you may not be asked to derive this equation, but even though it is worth deriving, you'll always be asked to use it in calculations. So we have arrived at the expression for the centripetal acceleration as being equal to V squared over R. So the centripetal acceleration is going to be V squared over R as shown there. But maybe just to take you further, I want you to recall that V is equal to omega times R as we saw earlier on, which means we can also say that the centripetal acceleration AC, of course this one you should always be able to show it. So V squared is going to be omega squared times R squared, and this is divided by R, which means the centripetal acceleration can also be equal to omega squared times R. So this can also be the expression for the centripetal acceleration. Also, we shall see that from Newton's second law of force is equal to mass times acceleration. So it means centripetal force is mass times centripetal acceleration. So we should be able to arrive at an expression for the centripetal force. Okay, so we have been trying to derive the centripetal acceleration. So I have already explained all this. At A, the velocity is VA. At B, the velocity is VB. The change in velocity may be seen as a vector diagram that I have showed. And the angle delta theta is small and measured in radians. So the arc length AB was approximated to be a straight line. Then the change in the vector delta V must be added to VA in order to give the new velocity VB. So that is to cause a change in velocity. So we use the similarity triangles and we're able to arrive at this. And suppose the time to travel either distance was the delta S or the angle delta theta was delta t. We divided both sides by delta t. So we divided both sides by delta t and we're able to arrive at the expression for centripetal acceleration as this. And from the expression that V is equal to omega r, we're able to come up with the expression for centripetal acceleration as that. And therefore, I said the centripetal acceleration can always be either quoted as this in calculation or omega squared times r many times. And if we consider Newton's second law, which is force is equal to ma, where m is the mass, since we now know what the centripetal acceleration is, then we can say centripetal force is going to be, where there is acceleration, I can put v squared over r, or I can put omega squared times r. So this is going to be the expression for what we call the centripetal force. So we have been deriving these expressions, but we have not defined centripetal force. neither have we defined centripetal acceleration. So let's define these two terms. So we shall define a centripetal acceleration as the rate of change of velocity for a body moving in a circular path, and it is directed towards the center of the circular path. The rate of change of velocity for a body moving in a circular path, and it's directed towards the center of that circular path. So we saw that the centripetal acceleration will always be calculated from this expression, or the centripetal acceleration will be given as omega squared times r. In calculations, we shall also use that. Then on the other hand, we have also talked about centripetal force. That force which keeps a body moving in a circular path to continue moving along its circular path, and it is also directed towards the center of the circular path, is what we call the centripetal force. The force is responsible for maintaining the object to continue in its circular path, and this force is what we call the centripetal force. It is always directed towards the center, just like the centripetal acceleration, as predicted by Newton's second law. That is, force is equal to mass times acceleration. Remember, the acceleration and the force, the resultant force and the acceleration always act in the same direction. So that is what we call centripetal force and centripetal acceleration. Okay. The other thing we may talk about now is application of the concepts, or application of the concept of centripetal force and centripetal acceleration. And I think this is the last part for circular motion. Application is the last part of circular motion. So applications of circular motion. Some of the common applications, like we have seen the Earth orbiting the Sun, so there is motion in a circle, and this is either going to be vertical, and it is going to be vertical or horizontal circle. So let's begin with application number one, that is motion in a vertical and horizontal circle. Motion in a vertical and horizontal circle. So I want us to consider a body moving in, let's say, vertical circle. I think we shall start with a vertical circle. Consider a body of mass, the mass is going to be m, moving in a vertical circle. Maybe it is attached on a string of length. Let's say the length of the string is r, which means the radius of the circular path is going to be r, and it is whirled in a vertical circle at a constant speed v. And then we are going to consider the motion of this body in different positions. So let's consider the mass of the object is m, and it is attached on a string whose length is r, because that is from the center, because the distance from the center to where the object is the length of the string. So the radius of the circular path is going to be r. So we should therefore explore the behavior, or we have to consider three positions of the body as it moves in the circle. Now what happens is that the tension in the string changes depending on the position of the object in the circle. For instance, in the first place here in position A, when the object is in position A at the bottom of the vertical circle, the resultant force F, which causes the centripetal force, which is supposed to be mv squared over r. The resultant force here is the difference between the tension which acts towards the center and the weight, which is going to be T1 minus mg in that position. So the resultant force when the object is in this position is T1 minus mg. So we say that at position A, the resultant force towards the center, which is the centripetal force, mv squared, is going to be equal to T1 minus mg. If we consider the object being in position B, note that the tension is acting at right angles to the weight, because the weight is always vertically downwards, which means the weight has no effect, has no impact on the horizontal force, which is the tension. So it means the resultant force towards the center in this case is only going to be equal to T2, and remember this is the one which provides centripetal force. So in position B, F is going to be equal to T2, which is simply mv squared over r. So the centripetal force in this position is the same as the tension in the horizontal. In position 3, the weight is acting towards the center, but the tension, remember tension always, the tension or the force, because the person pulling on the string is at the center of the circular path, then the tension is towards the center. In position 3, the resultant force onto the object is its weight, which is mg, plus the tension T3, and this is what provides centripetal force mv squared over r. So in all these three cases, if I call this F1, F2, F3, in all these three cases, you notice that the tension, the tension here, T1, is going to be equal to mg plus mv squared over r. And the tension here, T2, is simply mv squared over r. And the tension here, T3, is mv squared over r minus mg. It appears as if the tension experienced by the string when the body is in the position A is the maximum or is the greatest. That's why if a body is moving in a vertical circle, the string is most likely going to break when the object is just at the bottom. For an object moving in a vertical circle, the support or the string which is holding the object is most likely going to break when the object is at the bottom, because the tension it experiences is greatest when it is at the bottom. Of course, the tension is going to be minimum when the object is at the extreme top of the vertical circle. Okay, so we have explored the resultant force towards the center at every point. We have seen what happens at A, and we have seen the tension. We have seen what happens at B, and we have seen the tension. And we have seen what happens at C, and we have seen the tension. And we are noticing that the tension T1 is the greatest, because it is mv squared over r plus mg compared to the rest. So most likely the object is going to snap. The string is going to snap when the object is at the bottom. The string is going to break when the object is just at the bottom of its circle. Okay. So it can therefore be noted that tension in the string is maximum when the body is at the bottom of the circle, and it is minimum at the top of the circle. The tension is maximum at the bottom and it is minimum at the top of the circle. Therefore, if the tension is maximum at the top, so we say that the string is most likely going to break. The string is most likely to break when the body is at the bottom of the circle, because the tension is greatest when the object is at the bottom of the circle. So that is application number 1, which was the vertical circle. We have seen it in 3 positions, and we have been able to derive the tensions in the string at the bottom of the circle, at the top of the circle, and if the object is in the horizontal. Of course, someone will ask, how about if it is in the horizontal but on the left hand side? But before we move further, I want you to be reminded that wherever the object is, if the string breaks, remember it moves at a tangent to the circular path. It moves at a tangent because it moves in the direction of the velocity at that particular point. It always flies off at a tangent, but because of gravity, with the time, it will now move following that path. Okay. Let's now talk about a horizontal circle. I think from when we were starting this lesson, we saw a demonstration of a horizontal circle. This is an example of a horizontal circle. So where the center of the circular path is going to be at the point where the string is held. So this is moving in a horizontal plane above the head of the person who is describing this. So Remember, the weight of the object acts vertically downwards. So the only force which is pointing towards the center is actually going to be the tension. So it's like this is the only force which is going to provide the centripetal force. So in this case, for an object moving in a horizontal plane, we can't talk about any other position because at this point is in the horizontal, it is always in the horizontal at all points. Therefore, the only force, the force is always, the weight is always acting vertically downwards, and the tension is always acting towards the center because it is moving in a horizontal plane. So it means the centripetal force will always be mv squared over r, which will always be equal to the tension in the horizontal plane. So the forces acting on the object are the force of gravity, which is the weight downwards, and the tension in the string acting towards the center, which keeps the body in the circular motion. Note that the object's weight makes it difficult to make it revolve with the string perfectly horizontal. Because the object has some weight mg, the string may not be perfectly horizontal if you tend to make it horizontal, but because the angle is very, very small, then it is normally negligible. So we normally assume that the weight is small, and if the weight is small, it means the angle of depression, which is preventing the string to be perfectly horizontal, is going to be small and negligible. Otherwise, if it wasn't negligible, then we would draw something like this is the horizontal, then there is an angle delta theta somewhere there to the horizontal, which causes a depression. But because the mass is already small, then this angle here is negligible. Thus, tension will act nearly horizontally and hence provide the necessary force that gives the object the centripetal acceleration. So for an object moving in a horizontal plane, using Newton's second law, force is equal to msc, that is mass times centripetal acceleration, then F, or the force, centripetal force, is going to be just equal to the tension, which is mv squared over r. That is the centripetal force. So let's see a few examples. I think we have examples. Example number 1. Match these examples to the centripetal forces acting. Before we do the examples, I want us to remind ourselves of the formula that we may need in this case. Do not forget the ones we started with also, but we have already seen the centripetal acceleration is going to be v squared over r, which is going to be omega squared times r, and the centripetal force, which is m times centripetal acceleration, will simply be mv squared over r, or m omega squared times r. It is m omega squared times r. That will be the centripetal force. Okay, match these examples to the centripetal forces acting. A sock going around in a washing machine. So if it is a sock in a washing machine, what is providing the centripetal force is going to be most likely the friction, not the friction. I'll start with the simplest, those that we are very much aware of. A person on a rope swing, that is automatically tension. A Jupiter orbiting the sun, that is gravitational attraction, that is a planet. A lorry going around circular flat roundabout, that is friction. Then a sock going around a washing machine, that is reaction. It is actually the normal reaction. Normal reaction, which is actually the contact force. A sock going around in a washing machine is the normal reaction or the contact force, normal reaction force, which is the contact between the sock and the drum of the washing machine. Then a lorry going around a roundabout, there is friction between the tires and the road surface. A person on a rope swing, there is tension in the rope. Jupiter orbiting the Sun, the gravitational attraction or the gravitational pull of the Sun will make Jupiter to move around the Sun, to continue moving around the Sun. Okay. Example number 2, state an expression in terms of mg, s, and fc. For A, we have a car which is moving around a circular path, and the center of curvature is here. The radius of curvature is r, and it is over the top. It is on the top of the circular path. So let's see the resultant force towards the center of curvature is going to be the centripetal force. It is going to be mg, which is the weight. It is mg, which is the weight. Because here there is no tension, the only forces which are acting are the weight and the normal reaction force upward. So it will be mg minus s. That is the centripetal force. So this means mv, they wanted in terms of fc, s, and so fc is going to be mg minus s. That is the resultant force towards the center, or it would be mv squared of r equals to mg minus s. We are not having tension here because it is just a car moving on the surface of the road. So the forces acting are the weight and the normal reaction force, or the reaction force, which is upward. So the resultant force acting towards the center is the difference between mg and s. Let's see example number 2. Okay, the car is moving on the bridge. The weight is acting vertically downwards, and there is, of course, normal reaction force upwards, or the support force upwards towards the center of curvature. So the centripetal force Fc equals to the difference between the two forces. So it is going to be S minus the weight, which is mg. The resultant force towards the center of curvature is S minus mg, or it would be mv squared of r equals to S minus mg as required. Okay. Example. So these are now numbered examples. Example number 1. Since there is a force acting on the body, explain whether there is a work done on the body. Is there work done on the body since there is force acting on the body? Essentially, there is no work done on the body even when there is a force acting on the body. Now the question would be, why? How is that possible that there is a force acting on the body, but there is no work done on this body? So the force acting on the body, it is always acting at right angles. The force is acting perpendicular to the direction of motion of the body. The force, therefore, does not change the speed of the body, but simply changes the direction, providing centripetal force. So the force is always perpendicular to direction of motion, in brackets to the velocity. The force is always perpendicular to the velocity. Thus, does not change the speed, but simply changes direction. The force is always perpendicular to the direction of motion, thus does not change the speed, but changes direction. Hence, remember, work done is force times distance, and the distance is going to be the force is constant and is always perpendicular to the direction of motion, and thus does not change the speed but changes the direction, simply changes direction. Hence, we can simply say that there is no work done because the kinetic energy is going to be remaining constant since there is no change in speed. Hence, no work done. So the work done in moving a body around a circle by a certain force is actually going to be zero. So the force does not change the speed. It is because zero is perpendicular to the direction of motion. It does not do any work. It just changes the direction, but not the speed. So if a force cannot change the speed of the body, then we can say there is no work done. Then number two, find the acceleration of the moon if it travels at a constant speed of 1020 meters per second and takes 27.3. It takes 27.3 days for a complete revolution on the Earth. So we want the acceleration of the moon. So they have given us the constant speed. They have given us it takes 27.3 days for one complete revolution. So that is the period. So we know that centripetal acceleration is equal to v squared of r, which is the same as omega squared times r. Remember from our first part, we say that omega was equal to pi divided by t. So it means the centripetal acceleration is going to be equal to 2 pi divided by t, but this is squared, then times r. So they gave us the linear speed, and we don't have the radius, so I have to look for the radius here. Find the acceleration of the moon if it travels at a constant speed of 1020 meters per second and takes 27.3 days for a complete revolution. So I have the period. Okay, so of course this means the centripetal acceleration is going to be 4 pi squared over t squared times r. I think the earth to sun distance, the earth to moon distance are the distance between the sun and the earth and the moon is approximately 400 kilometers, which is approximately 3.844 times 10 to the power 3678 power 8 meters. So that is the radius, so I'll just use that one. So when I substitute, I have 4 pi squared times 3.844 times 10 to the power of 8 in meters. Divide this by the period is 27.3 days, so that would be 27.3 times 1 day is 24 hours, so that is 24. 1 hour is 3,600 seconds. Okay, so I'll press my calculator. 4 pi squared times 3.88. Let me see. 3 for kilo, 6, 7, 8. Yes, 3.8844 exponent 8 divide by 27.3 times 24 times 3,600. Okay, so the centripetal acceleration here is approximately 6433.9 or approximately 36400. meters per second squared. Of course, you don't need to remember this, it will always be given in the list. If it is required, it is always given. Okay, so let's see another example, number 3. A car is negotiating a circular track of radius 120 meters at 75 kilometers per hour. Calculate its centripetal acceleration. So we want the centripetal acceleration SC, which is v squared divided by r. They have given us the radius, they have given us the speed. We shall just change v from kilometers per hour to meters per second. So that would be 75 times 1000 divided by 1 hour, which is 3600. So that is v. I'll press my calculator. 75 times 1000 to change it to meters, divide by 3600. So this is approximately 20.8 meters per second. So this is going to be 20.8 squared divided by r, which is 120. So that one squared divided by 120. So the centripetal acceleration is approximately 3.6 meters per second squared. So that is the centripetal acceleration. Example number 4. A mass of 0.4 kilograms is rotated by a string at a speed v in a vertical circle of radius 1 meter. If the minimum tension in the string is 3 newtons, calculate the velocity, the maximum tension, the tension when the string is just horizontal. The tension when the string is just horizontal. I want you not to forget that maximum tension is when it is at the top of the vertical circle. That is when we have maximum tension. It's when it is at the top of the vertical circle. So the mass is 0.4 kilograms. The radius is 1 meter. The minimum tension in the string is 3 newtons. And we want to calculate the velocity, the maximum tension, and the tension when the string is horizontal. Okay. So I think I'll use this. I'll use the top of this. So max for the tension is minimum at the top of the string. So they gave us minimum tension as 3. So it is minimum at the top. And at the top of the vertical circle, if I remind you of the vertical circle, at the top, that's where we have minimum tension. Let this be the center. So this is where we have minimum tension. I'll call it T1. And remember, we said centripetal force Fc was mv squared over r, which was the resultant. The weight was acting vertically downwards. The weight was acting downwards, and the tension was also acting towards the center of the circle. So it is T1 plus mg. So it means T1 is equal to mv squared over r minus mg. So that is the minimum tension. So I'll just substitute. The minimum tension is given as 3. 3 is going to be m, which is 0.4, but this is v squared. Then divide by 1 minus 0.4 times g, which is 9.81. So this gives us v. So I'll just press my calculator. So my answer is 4.2 meters per second. So the speed is going to be 4.2, the velocity is going to be 4.2 meters per second. So this is 4.2 meters per second. Then the maximum tension, of course, maximum tension is when it is at the bottom here. We have seen this before. it is at the bottom here. Let's say this is T2. Remember, the weight is always vertically downwards, so the resultant is T2 minus mg. And the resultant is the centripetal force, which is mv squared over r. So maximum tension T2 is equal to mv squared over r plus mg. So I'll just sum up this. So this will be mv squared, which is 0.4 times 4.2 squared divided by r, which is 1, then plus 0.4 times 9.81. So 0.4 times 4.2 squared plus 0.4 times 9.81. So this is giving me 10.9 or approximately 11. So I'll just write 11 newtons approximately. Then the tension when the string is just horizontal. So when the string is just horizontal, this is the position here. So remember, when it is horizontal, the tension here I'll call it T3. The weight acts vertically downwards, so the weight has no contribution towards the centripetal force. So in that case, I would say T3 is simply equal to mv squared over r. So T3 is going to be 0.4 times 4.2 squared over 1. 0.4 times, I'm saying T3 is in the horizontal where the weight has no effect. So T3 is 0.4 times 4.2 squared, which is 7.0 or 7.1 newtons. So that will be the tension. I think that is true for example number 4. Let's check example number 5. A stone attached to a spring is moving in a horizontal circle. So here the circle is horizontal this time, of radius 96 centimeters. The stone has mass of 64 grams and completes one revolution in 0.72 seconds. Calculate the tension in the string keeping the stone in its circular path. So the stone has a mass of 64 grams and it is completing one revolution in 0.72 seconds. So this is the period. The period is 0.72 seconds. The radius is 96 centimeters, so this is r, and this is the mass. So calculate the tension in the string keeping the stone in its horizontal path. So in the horizontal path, because it's moving in a horizontal circle, it means the centripetal force is equal to the tension in the horizontal, which is equal to mv squared divided by r. So we have the mass, we have the radius, we don't have v, but we know that v squared is also equal to, or we know that v is omega times r, so v squared will be equal to this one squared. And we also know that omega is 2 pi over t, so this will be 2 pi over t times r, but this is squared. So it means the tension we are talking about here is going to be m. Where there is v squared, I'm going to put there 4 pi squared r squared divided by t squared. Then I again divide this by r. I just substitute for v alone. This is v squared. So one r cancels. So the tension is going to be the mass times 4 pi squared r divided by t squared. So I'll just substitute. So the mass is 64 by 10 to the power of minus 3 to change it to kilograms times 4 pi squared times r, which is 96 times 10 to the power of minus 2 to change it to meters. Divide this by the tension, by the period, not tension. This is tension. I want to distinguish these two. So this should be tension. One is period, one is tension. So this is period tension. So divide by the period, which is 0.72 seconds. So I have 64 exponent minus 3 times 4 pi squared times 96 exponent minus 2 divided by 0.72. So I am having the tension to be 3.36 or 3.4 newtons. It is 3.4 newtons. You can press your calculator and verify, but I'm getting 3.4 newtons. Example number 6. The drum of a spin dryer of radius 50 centimeters, so this is centimeters, 50 centimeters, and rotates at 720 revolutions per minute. Show that the angular speed of the drum is about 75 radians per second. So we have it rotates 720 revolutions per minute. So this is like frequency per minute. So frequency is going to be equal to frequency is 720 per minute. That is over 1 minute. I'm just going to change it to per second. 720 per minute is the same as 720 divided by 60 to make it per second. So the frequency is going to be 720 divided by 60. So the frequency is going to be 12 revolutions per second, which is 12 hertz. Now we want to find the angular speed. So that is omega. Omega is 2 pi over t, which is the same as 2 pi times f. So this is going to be 2 pi times 12. So 12 times 2 pi. So this is 75.4, approximately 75 radians per second. Then calculate for a point on the edge of the drum its linear speed. So the linear speed is V equals to omega times R, which is going to be equal to 75 times R, which R is 50. So this is going to be 50 times 10 to the power of minus 2 because it is 50 centimeters. So this is going to be 75 times 50 exponent minus 2. So this is 37.5 meters per second. Then its acceleration towards the center of the drum. So that is the centripetal acceleration. So SC is going to be equal to V squared over R, which could be 37.5 squared divided by 50 times 10 to the power of minus 2. So that one squared divided by 50 exponent minus 2. So the centripetal acceleration is going to be 2800 to two significant figures, that is meters per second squared as required. A toy train moves around a circular track of diameter 0.76 meters, completing one revolution in 12 seconds. So we can find the period here. If one revolution takes 12 seconds, in 12 seconds we make one revolution. That means the period is 12 seconds. Time for one revolution is 12 seconds. Calculate for the train the linear speed. So linear speed v is equal to omega times r, which is the same as 2 pi over t, then times r. So the linear speed is going to be 2 pi over the period, which is 12, times the radius, which is 0.76. So I'll pick my calculator. 2 pi times 0.76 divided by 12. So this is giving me the linear speed as 0.40 meters per second, or 0.398. Then the angular speed. The angular speed is omega. Of course, we know that omega is equal to 2 pi over period. So this is going to be 2 pi divided by 12. So 2 pi divided by 12. So this is 0.52 radians per second. Then the centripetal acceleration. So the centripetal acceleration SC is either v squared over r or omega squared times r. So I'll just say v squared of r, which is 0.40 squared, divided by r, which is 0.76. So to two significant figures, this is 0.210. Okay, 0.21. I want two significant figures only. Sorry. The units are meters per second squared. Okay. I think we have one or two more examples. A 500-gram mass is being swung around in a circle on a light string of length 50 centimeters. The speed of the bottom at the bottom of its string is 2 meters per second. Find the centripetal force required at the bottom of its string. So it is a 500-gram mass which is being swung around in a circle on a light string of length 50 centimeters. So the radius is going to be 50. So this is the circle. It is at the bottom somewhere here. The length from the position where the string is held to the object is 50. So that is the radius. And of course, the weight acts vertically downwards. The tension acts towards the center. So the difference between the two is the centripetal force. So the centripetal force S is going to be the tension minus mg. So that is the centripetal force, which is the same as mv squared divided by r. So we have the mass, and we have the speed at the bottom, and we have the radius. So I don't even need to calculate the tension. So the centripetal force is going to be, the mass is 500 times 10 to the power of minus 3 to change it to kilograms. And then V is 2, but is squared. Divide this by R, which is 50 times 10 to the power of minus 2. So 500 exponent minus 3, then times 2 squared, which is times 4, divide by 50 exponent minus 2. So this is giving me the centripetal force as being 4 newtons. I think that is the end of lesson number 2.